Thermal management is commonly used in applications like servers, telecommunication equipment, projectors, test equipment, and many more. In these applications, a thermal management system measures the ambient temperature of various areas in the equipment, also known as thermal zones, and controls the speed of fans to bring down the ambient temperature of these zones. In this video, let us have a look at how a thermal management system can be implemented using a PSoC 1 device. This block diagram shows how the thermal management system is implemented in PSoC 1. The PSoC measures the temperature of two thermal zones using a diode temperature sensor and TMP75, an I2C based temperature sensor. Using a temperature to speed table stored in the flash, the speed of the fans is calculated. The fans are then driven using two 8-bit PWMs. These fans provide tap feedback pulses at a rate of 2 pulses per revolution. The PSoC measures the speed of the fans from these pulses using a 16-bit timer and adjusts the PWM duty cycle to keep the speed of the fans within the desired tolerance. Let us have a look at the demo setup. This is the CY8C kit 001 PSoC platform kit with the CY8C28 family processor module. This is the CY8C kit 036 thermal management expansion board. The expansion board is connected to port B of the platform development kit. Fan 1 is connected to the first header and fan 2 is connected to the third header. A 12 volt 2 ampere power adapter is used to power the platform kit. J8 is configured for VREG. SW3, the VDD select switch, is configured for 5 volt. J6, the VDD analog select jumper, is configured for VDD. J12, the LCD power jumper, is configured for on. J11, the VR power jumper, is shorted. Jumper J9 on the thermal management EBK is configured for DBK power. In the breadboard area of the platform development kit, connect VR to port 01 and SW1 to port 16. Now let us have a look at the PSoC designer project. Port 01 is configured as an analog input to measure the diode voltage. In this demo, we are going to use the potentiometer on the platform kit to simulate a diode. Port 02 and port 03 are configured as the clock and data for the I2C master to interface with the TMP75 I2C temperature sensor. Port 10 is the PWM output for fan 1 and port 11 is the TAC input from fan 1. Port 14 is the PWM output for fan 2 and port 15 is the TAC input from fan 2. Port 16 is configured as a digital input with a pull-up resistor and is connected to the switch on the platform kit. Port 20 to 26 are configured for the LCD display. A hysteresis comparator is placed in ACC00 and the input of this comparator is connected to the analog mux bus. The tap feedback from the fans are multiplexed into this comparator. The output of this comparator is connected to the capture input of a 16-bit timer through the comparator bus. A unity gain PGA is placed in ACC01 and this PGA connects the signal from the potentiometer to a 14-bit incremental ADC. This ADC measures the diode temperature simulated by the potentiometer. A 16-bit timer is placed in DCZ02 and DCC03 and this timer is used to measure the speed of the fans. The capture input of this timer is connected to comparator bus 0. A 16-bit PWM is placed in DBC00 and DBC01 and the output of this PWM is connected to port 10 to drive fan 1. Another 16-bit PWM is placed in DBC10 and DBC11 and the output of this PWM is connected to port 14 to drive fan 2. Let us have a look at how the firmware is organized. Fan controller int.asm is an ISR for the 16-bit timer. Inside this ISR, the time between the rising edges of the takt pulses is calculated for each fan and the period value is stored in an array. The ISR also takes care of multiplexing multiple fan takt signals into the comparator. Fan controller low-level.asm implements low-level assembly functions used to initialize the takt system, get the period of takt signals, poll if a measurement is complete, read fan faults, and so on. At the end of this file, there is a table that stores the mux register and the bit mask values for each of the takt input port pins. In this project, we have two entries, one for port 11 and another for port 15. Fan controller.c implements high-level fan controller functions like calculate fan speed, set fan speed, get fan speed, closed loop speed control, and so on. This file also has a table that stores the fan parameters. For each fan in the system, this table has entries for minimum RPM, maximum RPM, two sets of RPM to duty cycle values, and a duty cycle to RPM slope value. Thermal manager.c implements the high-level thermal management functions used to measure the zone temperatures, calculate desired fan speed, update fan speed, and so on. In the beginning of thermal manager.c file, there is an array of structures called thermal lookup. For each zone in the system, this array stores the temperature to fan speed relationship. For this application, there are two zones. For the first zone, the fan runs at 5000 RPM for temperatures 0 to 15 degrees Celsius, 5500 RPM from 15 to 35 degrees Celsius, and so on till it runs at 10,500 RPM for temperatures above 75 degrees. Similarly, for zone 2, the fan runs at 5000 RPM for 0 to 30 degrees, 6000 RPM for 30 to 35 degrees, and so on till it runs at 10,000 RPM for temperatures above 45 degrees. Below the thermal lookup table, there is another array of structures that stores the parameters for each thermal zone. For each zone in the system, this structure stores the fan count, the fan IDs, the default fan speed, the method used to calculate speed from temperature, hysteresis, the number of temperature sensors, the sensor IDs, the method used to calculate the zone temperature, and the weight of each temperature sensor that contributes to the zone temperature. In this application, for zone 1, the temperature is calculated by using 10% of the I2C temperature sensor and 90% of the diode sensor, and for zone 2, the temperature is calculated by using 80% of the I2C temperature sensor and 20% of the diode sensor. Let us have a look at the application code in main.c. In the beginning of main.c, the global interrupts are enabled, the LCD is initialized, the thermal manager is initialized, and the pull-up resistor for the switch input is enabled. Inside an infinite loop, first the switch is polled to check if it is pressed. If the switch is pressed, the LCD mode variable is scrolled between displaying zone 1 status, zone 2 status, and the temperature sensor status. Next, the thermal manager service function is called. This function measures the zone temperatures, calculates the desired fan speed, and updates the fan controller with the desired fan speed. After this, the fan controller service function is called. This function measures the fan speeds from the ISR, calculates the difference between the actual speed and the desired speed, and modifies the PWM duty cycle to bring the fan speed to the desired tolerance. After this, depending on the value of the LCD mode variable, the LCD is updated with either the zone 1 status or zone 2 status or the sensor status. Let us now program the demo setup with a hex file. Before programming the code to the processor module, disconnect the thermal management EBK from the platform development board, connect the programmer to the ISSP connector of the processor module, power the kit, and program the processor using reset mode. Once the processor is programmed, switch off the power to the kit, insert the thermal management EBK to port B, and turn on the power to the kit. The LCD now displays the status of zone 1. It displays the zone 1 temperature on the first line and the desired and actual fan speeds on the second line. Turning the potentiometer on the platform kit changes the zone temperature and the fan speed can be seen updated. Press switch 1 to change the LCD display to show zone 2 status. Turning the potentiometer now changes zone 2 temperature and the fan speed is updated. Pressing switch 1 again shows the temperature sensor status screen where the zone temperature and individual sensor temperatures for each zone are displayed.